Most of reality hides in the shadows. The visible universe is only about 5% of everything that exists. The remaining 95% of is invisible to our eyes, yet it shapes galaxies, drives cosmic expansion, and scripts the fate of the cosmos. In this video, we lift the veil on the unseen, dark matter, dark energy, and the forces that you can't see but that rule the universe. We'll trace clues from gravity, radiation, and the cosmic web to show why the invisible actually matters and what it means for our place in reality. If you crave a fresh lens on existence, you're about to see the world in a way you never imagined. The visible universe and the hidden majority. Only a small fraction of what fills the cosmos shines as visible light. The luminous matter we can see, stars, planets, glowing gas, accounts for roughly 5% of the universe's content. About 95% remains invisible in the sense that it does not emit detectable light. Dark matter alone makes up about 27%, while dark energy contributes around 68%. What we observe is the bright tip of a much larger gravitational structure that holds everything together. We infer the unseen through its gravity and its influence on motions and light, even when no photons come from it. Galactic rotation curves, for instance, rise and then flatten, signaling extra mass beyond the stars. Gravitational lensing maps reveal hidden mass that bends the light from background galaxies. Neutrinos slip through almost everything, including dense detectors, carrying energy from the heart of stars and distant explosions. They are part of the invisible messengers that remind us reality is bigger than what eyes can see. Dark matter candidates like WIMPs or axions would interact so faintly that only careful underground experiments or indirect signals could catch them. Detectors chase tiny recoils or unusual photon signatures. They have not yet found definitive evidence. In the meantime, the gravitational footprint remains the strongest clue. Halos around galaxies serve as massive, invisible anchors for rotating stars and gas, shaping the dynamics we observe. Dark energy is space itself filling with a mysterious energy density that resists compression. It nudges cosmic expansion to accelerate, a behavior that seems to be uniform across space. This hidden component governs the universe's fate and modifies how structures grow on the largest scales. The visible universe, framed by galaxies and clusters, depends on the invisible majority to shape its architecture. Understanding it challenges our theories of gravity, quantum fields, and the vacuum. The 95% majority is not just a backdrop. It is the active force that organizes the cosmos. To study the invisible majority, astronomers combine light from many wavelengths, gravitational bending, and timing of distant signals. Weak lensing surveys reveal subtle distortions across millions of galaxies, stitching together a map of dark matter scaffolding. Cosmic background measurements pin down the energy budget and the geometry of the cosmos. Gravitational waves and neutrino astronomy add new senses that detect phenomena where light would be faint or blocked. Upcoming surveys and detectors aim to pin down the nature of dark energy and the composition of dark matter, bringing us closer to a complete census of reality. The visible universe remains the glass you can hold, but the hidden majority is the gravity and the energy that hold it all together. The 95%, dark matter and dark energy. About 95% of the universe's content is invisible to direct observation. The rest is ordinary matter that forms stars, planets, and everyday objects. Dark matter and dark energy dominate the cosmos. We infer their presence from gravity and the expansion of space. Galaxy rotations, gravitational lensing, and the cosmic web all point to unseen actors shaping the universe. In the standard cosmological model, roughly 27% is dark matter and about 68% is dark energy, leaving around 5% as the ordinary matter we interact with. Dark matter acts as an invisible scaffolding for galaxies, clusters, and the large-scale structure. It does not emit, absorb, or reflect light, in any significant way. We infer its existence from gravitational effects and from the way light from distant objects bends around unseen mass. Evidence comes from the rotation speeds of galaxies that stay far from their centers and from the way clusters hold together in ways ordinary matter cannot explain. The leading idea is that dark matter consists of particles that interact weakly with light and ordinary matter, routed through gravity more than anything else. Experimental searches range from deep underground detectors to astronomical observations, yet direct detection remains elusive. Dark energy drives the accelerated expansion of the universe. Its nature remains puzzling, and it behaves like a property of space itself rather than a substance you can pick up. It has a nearly uniform density that stays constant as the universe grows, gradually pushing galaxies apart on the largest scales. The cosmological constant is the simplest explanation, representing a fixed energy density of empty space. More dynamic possibilities exist, but they must align with precise measurements of how the expansion rate changes over time and how structure forms under gravity. Understanding dark matter and dark energy changes how we interpret cosmic history and the fate of the cosmos. Surveys of galaxies, supernovae, and the cosmic microwave background test these ideas and sharpen the parameters that describe the unseen components. Particle physics experiments, gravitational lensing maps, and simulations of structure growth collaborate to pin down what these components are and how they interact, even if only through gravity. The 95% remains largely invisible, yet its fingerprints are everywhere, shaping the paths of photons and the movements of every galaxy. The pursuit continues as new detectors and telescopes probe deeper and map the unseen more clearly. Evidence across scales, from galaxies to the cosmic microwave background. Galaxies rotate faster than their visible mass would allow. The rotation curves stay flat at large radii rather than declining, signaling a hidden mass component enveloping the galaxies. In many spirals, stars far from the center trace gravity from an extended halo that does not emit light. This conclusion comes from systematic studies across many systems, not from a single odd example. The result is a coherent picture in which gravity reveals an invisible majority around ordinary matter. Galaxy clusters amplify the story on bigger scales. The hot gas that fills clusters shines brightly in 10th rays, and its temperature distribution maps the deep gravitational well. Galaxy motions and the bending of background light show there is far more mass than the visible galaxies and gas can account for. Gravitational lensing provides a direct measure of total mass along the line of sight, independent of the matter's state. In well-known cluster observations, the mass mapped by lensing aligns with dark matter's distribution rather than with the hot gas, indicating a collisionless substance distinct from ordinary matter. On the largest cosmic stages, the distribution of matter follows a vast web shaped by gravity. Weak gravitational lensing, or cosmic shear, paints maps of the dark matter skeleton that threads through galaxies and clusters. Numerical simulations that include a non-luminous component produce filaments and halos that resemble what the sky shows, reinforcing the idea that invisible mass seeds and guide structure. Baryon acoustic features seen in galaxy surveys act as standard rulers in the expanding universe, linking the distribution of visible matter to the underlying dark matter framework. Taken together, these observations across scales, galaxies, clusters, and large-scale structure point to a pervasive invisible mass shaping cosmic fate. The cosmic microwave background offers a snapshot of the early universe that ties all scales together. Temperature and polarization patterns reveal primordial fluctuations carved into the photon-baryon fluid before recombination. The distinct acoustic peaks encode the balance between ordinary matter, dark matter, and the geometry of space, so the data require an invisible component beyond what shines. Lensing of the CMB by intervening mass distorts the primordial signal in a way that maps the integrated gravity along the line of sight. The convergence of information from the CMB, galaxy surveys, and gravitational lensing creates a consistent case for unseen components governing the growth of structure, from the smallest spirals to the largest networks in the cosmos. Probing the invisible. Observations and experiments. Only a fraction of a universe's content shines in visible light. Most of it remains invisible, made up of dark matter, dark energy, stealthy neutrinos, and gravitational phenomena that do not emit photons. Probing this invisible realm relies on indirect signals, gravity, particle interactions, and subtle space-time distortions. Scientists design experiments to catch whispers from the unseen and translate them into maps we can study. Gravitational lensing reveals unseen mass by bending light from background galaxies. Weak lensing surveys detect tiny distortions across vast swaths of the sky and assemble maps of dark matter halos. The polarization of the cosmic microwave background offers clues about the universe's composition and its early dynamics. Neutrino observatories like IceCube capture high-energy neutrinos that traverse the Earth, pointing back to their cosmic sources. Gravitational waves from merging compact objects add a second messenger channel for gravity. Together, these signals create a multi-messenger view of phenomena that otherwise stay invisible. Direct detection experiments hunt for rare interactions between dark matter particles and nuclei. Underground detectors use massive vats of xenon or argon in ultra-pure environments to minimize noise and maximize the chance of a collision. Examples include XeNT, LZ, and PandaX. They look for faint scintillation and ionization signals that would indicate a particle passing through the detector and nudging a nucleus. So far, no conclusive dark matter signal has emerged, but the resulting limits narrow the possible properties of these elusive particles. Imaging the invisible is not limited to particles. It also includes shadow and wave phenomena. The Event Horizon Telescope translates horizon-scale structures into still images that confirm the existence of shadows cast by black holes. Gravitational waves expand this reach, revealing mergers and the dynamics of space-time across the cosmos. Pulsar timing arrays search for very low-frequency gravitational waves by monitoring the regularity of pulsar signals. Plan for future instruments and networks, such as the Square Kilometre Array, promise broader surveys of neutral hydrogen signals that trace structure across cosmic time. In parallel, 21cm cosmology aims to map the universe's dark ages and reionization era by tracking neutral hydrogen. These strategies collectively advance a coherent picture of the invisible universe and test ideas about dark matter halos, dark energy, and the fabric of gravity itself. Implications for physics, technology, and understanding. The majority of the universe's energy content is invisible, comprising about 95%, with dark matter and dark energy as the main components. Dark matter exerts gravity in galaxies and clusters, shaping rotation curves and structure while remaining unseen. Dark energy drives the accelerated expansion of the cosmos, acting as a universal repulsive force that changes how structures spread over time. These invisible constituents push physics beyond the standard model, prompting new theories and experimental approaches. Observational signals come from gravitational effects, from the cosmic microwave background, and from large-scale structure, not from direct optical detection. To reach the invisible, experimental physics builds ultra-sensitive detectors buried underground in shielded facilities that minimize background noise. These detectors often use cryogenic temperatures and noble liquids to capture rare interactions. Calibrated instrumentation tracks minute energy deposits and faint scintillation light, seeking signatures of dark matter particles traversing Earth. Many projects rely on precise timing and large arrays to distinguish signal from background. Advances in laser interferometry, superconducting sensors, and quantum-enhanced readouts expand the reach of gravitational waves and other subtle messengers. Theoretical physics must adapt as evidence accumulates. Candidates for the unseen include particles beyond the standard model, such as weakly interacting massive particles or axions, and new ideas about hidden forces. Alternative gravity models, evolving dark energy scenarios, and the possibility of a richer dark sector motivate a broader research program. Cosmological data from lensing, galaxy surveys, and the cosmic microwave background constrain these ideas. The challenge is to build a consistent narrative that explains both laboratory results and cosmic observations. Understanding the invisible universe reshapes how we design experiments and interpret evidence. Cross-disciplinary collaboration becomes essential. Data science, simulations, and theory feed each other as researchers test ideas against diverse datasets. Technology spin-offs appear in sensing, imaging, and precision measurement that benefit other fields and industries. A robust program asks for sustained communities, open data, and careful, transparent methods so tiny signals can be trusted. Frontiers and future prospects. About 95% of a universe's energy content is invisible to ordinary telescopes and everyday perception. The invisible portion splits into dark matter and dark energy, two mysteries that sculpt cosmic structure and expansion even though we cannot see them directly. Evidence for dark matter arises from galaxy rotation curves, gravitational lensing, and the patterns of the cosmic microwave background, while dark energy reveals itself as the acceleration of the universe's expansion. The frontier is not a single puzzle, but a landscape of interlocking questions. What are the particles or fields behind darkness, and how does their behavior shape galaxies, clusters, and the fate of all cosmic structures? Direct detection efforts aim to catch dark matter particles as they pass through Earth, turning a quiet burp of rare interactions into measurable signals. Experiments such as large liquid xenon detectors pursue signals from WIMPs, if they exist, by watching for tiny flashes of light and heat when a particle collides with a nucleus. Parallel searches hunt axions and axion-like particles with resonant cavities and precision magnetometry, try to catch extremely weak couplings predicted by certain theories. Colliders push boundaries by producing high-energy environments where dark matter particles might be created and escape, leaving telltale imprints in missing energy signatures. Indirect detection looks for secondary products, like gamma rays or antimatter, produced when dark matter particles annihilate or decay in the cosmos, with telescopes surveying the center of our galaxy and other bright regions. Gravitational phenomena offer a different route to the unseen, complementing particle hunts with a gravity-centered view of the universe's skeleton. Gravitational waves carry information about massive, energetic events and, in principle, about the very fabric of space-time during epochs inaccessible to light. Ground-based detectors have already opened a new window by catching mergers of black holes and neutron stars, while future space-based observatories will access a gentler, lower-frequency band that traces early universe processes and the growth of colossal structures over time. These waves act as standard sirens, helping to measure cosmic distances and the expansion history in concert with electromagnetic observations, thereby constraining dark energy's properties and the sum of neutrino masses that subtly bend space-time. The road ahead hinges on coordinated observations across wavelengths, messengers, and disciplines. Large optical and infrared surveys map how dark matter threads through the cosmos by weak gravitational lensing and galaxy clustering, revealing the invisible scaffold behind visible galaxies. Space missions and ground-based facilities will work together to chart the geometry of the universe, test gravity on cosmic scales, and search for deviations from the standard model of cosmology. New 21-centimeter experiments aim to illuminate the cosmic dawn and the transition to later eras, offering a three-dimensional map of hydrogen that traces structure formation as the universe cools and evolves. Advances in simulations and theory will refine our models, help distinguish dark matter candidates, and test alternative ideas such as self-interacting dark matter or modified gravity. Ultimately, progress will come from a fusion of technologies and ideas. Highly sensitive detectors, expansive sky surveys, and robust multi-messenger networks that combine light, gravitational waves, neutrinos, and cosmic rays. The implications reach beyond astronomy and into fundamental physics, potentially revealing the particle nature of dark matter or the true character of dark energy. As experiments push into deeper sensitivity and collaborations connect disparate data streams, the invisible universe begins to yield its secrets piece by piece, reshaping our understanding of reality itself and the story of how everything we can see sits inside a much larger, mostly unseen cosmos. Here is the takeaway. Only a slim sliver of the cosmos, the light we can see and the matter we can touch, belongs to the 5% of ordinary matter. The rest, about 95% hides in the gravitational shadows of dark matter and the dynamic pull of dark energy, shaping galaxies and bending the fabric of space. We don't see them directly, but their fingerprints are everywhere, from how galaxies rotate to how light bends, from the afterglow of the Big Bang to whispers for neutrinos and gravitational waves. If you felt that pull to know more, you're not alone. Watching this, you're taking part in a long human conversation with the universe, learning to listen with instruments and curiosity. The invisible is not a distant mystery. It's a frontier we study together, step by step. If this journey sparked your curiosity, subscribe for more episodes that chase the unseen. A like or a share helps others join the conversation, and your thoughts in the comments can steer what we explore next. Next time, we'll dive into the main contenders for dark matter, what gravitational waves tell us about the invisible, and how new detectors could reveal fresh facets of dark energy. We'll meet the researchers, unpack the ideas, and imagine discoveries that could reshape our sense of reality. Until then, keep looking up and keep wondering. The invisible universe is part of our everyday reality, and together we're learning how it fits,